I forgot to turn my microphone on, so I'm just going to have to narrate this. We'll see how it goes. It's not going to be live narration anymore. It's going to be narration after the fact. So this problem has two non-conducting wires charged. Oops, step back. The one short wire is positively charged. The other one is negatively charged, and they are at right angles with respect to each other. I'm just going to tell you that because this wire is not infinitely long, neither of these is infinitely long, that we're going to have to use Gauss's, we can't use Gauss's law, we're going to have to add up point charge by point charge. Take differential elements of the wire, calculate the point charge for each differential element, and then integrate that over the whole wire. A quick picture of why you can't use Gauss's law to find the electric field, not easily at least, to find the electric field due to this finite length positively charged rod at point P. Because it's a rod, you might think of using cylindrical symmetry. In fact, you might draw a cylinder around that, a Gaussian surface that's a cylinder around that rod. So that the surface intersects point P as a way of finding the electric field at point P. The problem with that is that the electric field on this Gaussian surface not only doesn't have the same magnitude everywhere on the surface, but it also doesn't have the same direction. At point P and the opposite side, it's nice because it's perpendicular, which is what you would like. But when you go to the sides of this cylinder, you find out that the electric field points somewhat away from the positive charge and certainly is not perpendicular to the cylindrical surface. So this is not going to work. Gauss's law is not going to make it easy for you to solve for the electric field here. And we're going to have to do the integral. So let's think about doing the integral. Take a differential element, it's like a point charge, differential element. The field due to that differential element will point, because it's a positive charged element, will point away from the rod. At point P, it'll point in a direction shown there. This differential element I'll call dl. We need to find the Q associated with that differential element, so a differential Q, and that would be the linear charge density, Q over the total length, times dl. The linear charge density times the differential length is the differential charge. The electric field due to that point charge has drops off as 1 over r squared. R is the distance from the point charge to point P. And so the differential element, the differential electric field, the tiny electric field due to dq is dq over 4 pi e0 r squared. R squared we'll have to write But we also have to remember that the electric field points away from there's the R vector. The electric field is a vector, so we need components. We need an x component and a y component. We should calculate the two separately. This is a normal kind of coordinate system, has x as a horizontal coordinate, y as the vertical coordinate, and we would want to calculate the two separately. The nice thing here is that the y component, as you go along this thing, the y component is always negative, and the x components of the various pieces cancel each other out. So we end up without an x component from this positively charged bar at point P. At other points there will be an x component, but the point P is right in the middle. Symmetry of the problem tells you, once you think about it, tells you that there won't be an x component. That's the electric field vector I've drawn there from that one differential element, dq. And we want to add that up over the whole length of the bar. Just writing in an angle there, theta, because we're going to need to get the x and y components. Of course, we're not going to, we can write down the x component, but if we did the integral, we would find out it would cancel. So, although I'm going to write it down, I'm not going to worry about that because I already know it's going to cancel. Sine theta is going to depend on the x coordinate of the x coordinate of the rod. There's your coordinate axes. Theta is going to depend on the x coordinate of the rod and the distance, the y distance to point P by normal kind of trig relation. And so when you write that out for theta, and you write out r in a similar way, depending on those two, whether you're talking about the x coordinate of the bar and the y coordinate of point P, both of those go together to give you r, which changes, the length r changes as you move from the left-hand side of the positive charged rod over to the right-hand side. In other words, as you integrate over the left-hand side over to the right-hand side.